spaces, a Riemannian perspective. So now, Oliver, you may start to talk.
Okay. First, I got thanks to Douglas to inviting me to give this talk. And we have already seen there are a lot of very good speakers. They give a lot of good talk. So I guess my talk would just, like a chill little bit. And I might just introduce some basic geometry on homogeneous space. And most of those perspectives are on Riemannian cases. So I'm gonna start right at first. This is the table of contents. And in the first of this talk, I might just introduce the basic definitions about the homogeneous space and in a geometric way and in a algebraic way. Like we have already seen, the homogeneous space is definitely have a lot of manifold background, also with the group structure. So it follows, I'll give a bit examples about the homogeneous space. Some of them are just normal things, and some are just not. And for those algebraic structure which lives in the homogeneous space will be introduced in section 3. And in section 4, I would just establish some Riemannian settings, including those Levi-Civita connections and how to calculate them is the most important things. And as an examples, I'd like to demonstrate how the interaction between the Lie theory and the homogeneous space in a geometric way. I will use the example of complex structure with the root systems. Okay, let's start with the first part, the definitions. At first, we let M be an n-dimensional smooth manifold with or without a boundary, and G be a Lie group. A little bit, okay. And we just denote group action on the left. It will see the G dot M here is just in a formal case. We call this M is a homogeneous space if the group action is transitive. Um, this which means for any 2 points in this manifold, you can have a element in G that you can connect the M1 and M2. It feels like for example, you're in an airport and you can take any plane to anywhere of this world. And if we fix 1 point in the manifold, we denote isotropy group. It is a closed subgroup that we can write in this form. The closeness is obvious because they just map 1 point to a single point. So there is a diffeomorphisms on this quotient space on the left and this manifold. This diffeomorphism obviously they got an inverse. You can choose the G inverse to get an inverse map. So in this way, we can identify the M with G mod GM. Okay, and in an algebraic way, let G be a connected Lie group. We here basically we're talking about a Lie group with finite connected components, and H B is a closed subgroup. The quotient space is called homogeneous space. Is a coset, for example. And also the Lie group G act on the G mod H as a group product. As you can see, it just left product about this group. Okay. For the first informal, we just write G action on the left, and it's there is a lot of things that a lot of group that might just not a left action. For example, we can make a counter examples about the joint action. When you write it down, you can see it's a G H G inverse, right? And the second remark, we can see the G mod H, it got a quotient topologies and is a smooth manifold. We can took the smooth structure with the principal fiber bundle structures. You can see G is a bundle and I H the fiber and G mod H the base point. base space and with a smooth subversion. So it actually is a smooth manifold. Okay, for those examples, the first example is kind of trivial. You can use the matrix group, and the group action on the left is just a matrix product, right? For the less trivial things is for those there are a lot of homogeneous space. They got the same properties with the Lie group, and the Lie group is just like a is a homogeneous space with a trivial quotient. So there, if you arrange those things correct, you can pull the Lie group properties to the homogeneous space. But in some case, we cannot make that. And the second examples is about n-dimensional sphere. We can choose the orthogonal group, n-dimensional orthogonal group, act on Sn is a linear transformation. And when we fix the North Pole and we chose the subgroup H, it's just a rotation to fix the North Pole and just rotation the whole sphere, and it just acts astrophically on the North Pole. So we can identify the Sn with the On quotients On minus one. Okay. The third example is symmetric space. It's a kind of algebraic setting, and we have already seen in the early of this conference. They got a lot of interesting things in symmetric space. So I just call them algebraic settings about it. And for the G, the Lie group, and H is closed subgroup, and we can choose the automorphisms on the Lie group, such that it when you make it two times, act two times on the same element, it's just identity. The first property we might just call it the involutive, and the second is just that for the fixed point set, this is a set might not be it is a subgroup, but we do not choose the whole. We just chose like identity component, and which is a subset of H and a subset of G theta. We just use this H. Then G mod H is called a symmetric space. Okay. With those things, we might just introduce some algebraic structures on it. Okay. In the algebraic setting, G mod H being a homogeneous space, we got a Lie algebra H and subalgebra. Lie algebra G and subalgebra H. Um, and then for the canonical projection, we use the differential of it. It, it works on the Lie algebra G and uh, to the tangent space at identity. And for any Lie algebra G element X, it works like this. And we can express this action with an exponential map. This is just a one parameter subgroup that generated by the exponential map. Okay, in this way, since the edge is the isotropy part, so the kernel of this canonical projection is just edge. And we just identified G mod edge with the identity with the tangent space at identity E edge. Okay, and in general, we just make correspondence. In here, we might not just assume it might not be a 1-1 correspondence. So we just write it like this. This part, reminder of this part is very useful. Okay. In general, we might not just identify the vector space Gmod H with all the vector files on the homogeneous space by this left action G. This because this is difference with the Lie group. When you take all the when you take vector files locally, you can write it down with the basis and entry functions. Those entry functions might not be G invariant. So also the G mod H might not be a might not be a Lie algebra. The bracket that inherit by the vector files might not just be closed. So we need more informations. So let's give a little bit deeper definitions about that. We call the homogeneous space G mod H is reductive if the G admits a ADH invariant vector space decomposition, and we can write the decomposition in this form. So the reductive conditions, which we means the ADH invariant conditions, just make sure that the decomposition of each X in the M is unique. So the decompos in this case, the decomposition above is just a direct sum as vector space. So we can identify M with G mod H, the tangent space of G mod H and identity with this map. This is a one-to-one correspondence. And with this ADH invariant properties, it's pretty useful. So we might introduce the isotropy representation on it. It's just a adjoint action of H that acts on the tangent space like a G mod H. You can see in general case it just write in this way. But if G mod H is reductive, the isotropy representation is nothing but ADH action on M, because we might not just confuse with this part, with this part. Yeah. Okay, let's go to the Riemannian case. Let G mod H be a homogeneous space. Okay, for if there exists a Riemannian metric such that for the G in big G is an element in a Lie group. X hat, Y hat is vectors in the tangent space at identity that just connected to the Lie algebra in G. So we might write if the Riemannian metric that satisfies these settings, we call this Riemannian metric is G invariant. Here, I might say a little bit because in this way, we just chose the action is just on the left. And because we just write the homogeneous space in this form in the Lie algebra, in Lie group setting. If we just write it in the geometric way, the action here is just the G action. No need to be the left. No need to be on the left. Okay. Thanks to the Mayers and the Stiernord, we can always find a homogeneous structure on the Riemannian manifolds. So this is the well-known Mayer-Stiernord theorem. It states that in a connected Riemannian manifold, let's say the M and G the Riemannian metric, then the isotropy group, no, sorry, the group of isometries that which is those diffeomorphisms that preserve this Riemannian metric. And these isometric groups, they just admitted a differentiable structure. And those group of isometries is a Lie transformation group of this Riemannian manifold, which means for any element in this group, it just induces a transformation on the manifold level. And this transformation is they preserve the Riemannian metric. Okay. And the isometry group is pretty big, but we don't need the whole isometry group. In the Riemannian cases, if we just assume that the manifold have finite number of connected components, and the isometry group is also acting, the identity component of isometry group is also acting transitively on them because like we just said, the G mode H is a diffeomorphism of M. So if the M is compact, then G is compact. If the M is have finite number of connected components, then G does. So it's no harm to use the identity component of this isometry group. Okay, let's express some basic properties about those invariant metric on G mod H. This proposition, you can find it in any books about differential geometry and Lie theory, and it's just shown in Kobayashi's book. So for those all, there are a lot of invariant metric on G mod H, but we gotta chose it to fit our Lie algebra. So there is a one-to-one correspondence between the G invariant Riemannian metric, like in this bracket, on the G mod H with ADH invariant, not degenerate symmetric bilinear form, which we might just say ADH invariant inner product. Let's say this inner product, let's state B on this quotient space. So the B satisfy these equations, which means the Riemannian metric, uh, sorry, the value of the Riemannian metric at identity is nothing but a value of ADH invariant inner product on its Lie algebra level. So we just establish some connections between the manifold and its Lie algebra. If G mod H is reductive, then the correspondence is given by in this way. And here X, Y just belongs to G, and X, Y with a lower mark are just elements represented by X and Y. Okay. This vector file we have already seen before. So let's give it a new name. Let GH be a G mod H be a reductive homogeneous space, and this is Levi-Civita connections. We call this vector files the Killing vector files. This vector files is just generated by the one parameter subgroup of isometries, and it got a very good property to use it to calculate. We got this proposition. This proposition is you can find it anywhere in the books. You can see we just send everything from the Riemannian manifold to its algebra level. And this U is a two form that denote in this way. Okay. If we make a more strict restriction, let's say we have this reductive decomposition is orthogonal with the inner product. We might say this decomposition is naturally reductive. In this way, the U just nothing but zero. Okay, let's make examples to use the Lie algebra structures with to how it works on the manifold level. Let's just make some definitions. G mod H be a reductive Riemannian space. We call the isotropy representation. ADH is completely reducible. It's nothing but a representation and a model setting. If M can have the decomposition as irreducible models in this way. Okay. And the above can be orthogonal by giving an ADH invariant inner product. this inner product is always exist, and this inner product can be written as G. As we have seen before, when you denote ADH invariant inner product, you have a G invariant metric on the manifold level. So equally we just give uh, expressions about the G invariant metric on the homogeneous space. Okay, let's go to the almost complex structures. As we have already know, is a one-one form, one-one vector files, such that G when it act in two times, it just minus identity. Okay, and the decomposition in this way, and the integrabilities is just Levi-Civita connections with G is 0. And we just make a definition to make it into our homogeneous settings. The G invariant almost complex structure are the on a reductive homogeneous space. It's just the almost complex structure that commute with the joint action of H. And we just make some examples about the generalized flag manifolds. Okay, what is generalized flag manifolds? Let G be a compact and a connected Lie group, and H be a closed group, a closed subgroup, which is also compact. And the homogeneous space G mod H is called a generalized manifold if the H is a maximal torus. Is a torus, but not need to be maximal. Sorry, when the H is maximal torus, which is let's say what the Cartan subalgebra, it's called a flag manifold. And if G is simple Lie group, we have the root decomposition in the complexifications in here. Here, the root decomposition, it can be decomposed in M, in the roots that belongs to M and belongs to K. So we can write the whole root space in this way. Okay, and here comes the proposition. There is a one-to-one correspondence between the G invariant complex structures and the G invariant order on the smooth space Rm plus, but it's nothing but a positive root in this way. So as you can see, it just create a complex structure here. Okay, here is the examples. The SU3 multi-2 case. Here, the G mod H is just a flag manifold, and the representation, isotropy representation, decomposed into three irreducible summands. Each of those MIs are irreducible in real two-dimensional. So we can write the complexifications like this, and H is a Cartan subalgebra. So we just state the root decomposition in this way. It's an order of G invariant, which means that if you act on the act G on the left, the order is not gonna be changed. So there is a G invariant complex structure we can write in this way. There is a one-to-one correspondence with a root space decomposition. So okay, here is some references, and I think I might just stop right here.
So okay, let's thanks for the Oliver for his wonderful talk. So is there any more questions about this talk?